Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Introducing RudderStack Profiles. RudderStack Profiles takes the SAS guesswork and SQL grunt work out of building complete customer profiles so you can quickly ship actionable, enriched data to every downstream team. You specify the customer traits, then Profiles runs the joins and computations for you to create complete customer profiles. Get all of the details and try the new product today at dataengineeringpodcast.com/rudderstack. You shouldn't have to throw away the database to build with fast-changing data. You should be able to keep the familiarity of SQL and the proven architecture of cloud warehouses, but swap the decades-old batch computation model for an efficient incremental engine to get complex queries that are always up to date. With Materialize, you can. It's the only true SQL streaming database built from the ground up to meet the needs of modern data products. Whether it's real-time dashboarding and analytics, personalization and segmentation, or automation and alerting, Materialize gives you the ability to work with fresh, correct, and scalable results, all on a familiar SQL interface. Go to dataengineeringpodcast.com/materialize today to get 2 weeks free. Your host is Tobias Macey, and today I'm interviewing Andrei Tserakhau about operationalizing high bandwidth and low latency change data capture. So, Andrei, can you start by introducing yourself?
Hello, my name is Andrei. I'm working as an engineer for quite a lot. I think it's more than 10 years now. And for last, I would say like maybe 6, maybe 7 years, I work for this mainly on distributed systems and mostly focusing of data movement stuff, moving data from point A to point B somehow, somewhere, with some data. And I'm actually specializing in it. I have quite a big journey before, but right now I'm mostly focusing on this stuff. And I think I have quite a good experience in this area from my past.
And do you remember how you first got started working in data engineering?
Actually, it was quite a fun story because initially I have my own startup, which is boring one. We'd be building the bus transportation application, bus in terms of like cross city bus, international buses, something like this. This startup was fine, everything was quite okay. And at some point, a big corporation buy out our startup, and after a year inside of this big corporation, they decide to close the startup and they proposed me to change my role. And actually, after so many years working in this fascinating from terms of a business area, but not so interesting in terms of a technology, to change my role. And I decided to change to more technical stuff. I always love working with the databases and decided to go to the infrastructure team. Mostly it was data infrastructure team. And I start working on the project that actually quite old. I would say 15 years before. Once I joined, has already 15 years of history, something approximately like this. And it moved a lot of data from a lot of different sources into one big data warehouse. This data warehouse was extremely big. And my goal was to make delivery lag a bit less than it was before. And this was the initial touch of anything in data engineering field. I think it was 2016 or 2017, something about this. And at the moment, the product that move this data utilize a lot of pretty old but still quite good concept as a map reduce. So there was like two main pieces of this software. One, it's like delivering data from actual producer of the data. It's usually application to a sort of a queue. It was not a Kafka because Kafka was not able to handle such load. It was internal replacement of a Kafka. It has some Kafka flavor. For example, topics still named as with a Kafka prefix, but it's implemented in a C++ to make it little bit faster. Right now, I don't remember what exact number of traffic was in 2016, but in 2018 it was about 5 gigabyte per second. It's amount of traffic that incoming into the system, and this traffic goes from the applications. Usually, it's written somewhere and deployed somewhere in the cluster, and they provide the logs, and these logs need to be delivered into the data warehouse in a structured way as fast as possible. But initial design was like we have this application. It provide data into the queue. From the queue, we provide this in a rough format in a data warehouse, and then we have a huge pipeline of MapReduce jobs that parse this data, index this data, and publish this data as a final tables. And this whole pipeline was quite a big scale. At the end, it generated like 5 or 7 thousand different kinds of tables, and amount of data was extremely high. It's a dozen of petabytes of data, so it's quite extreme load. The problem with whole this approach, it was very good in terms of scalability. It scaled quite well on horizontally because it utilized MapReduce approach. It just chunked of raw data by some size, then transform it somehow, parse it somehow, index it somehow, push it in a table, and then get another chunk, etc., etc. But delivery lag between the actual event on the machine, on the application, and the uh, final table, delivery lag was quite high, about 5 or 6. It was constant one, so it's not growing anytime. It always 5 or 6 hours. It's actually not doesn't matter if your table big or small. It's always 5 or 6 hours. It's like constant tax for your data. I think this approach is more or less well known because it's like batch processing, big batch processing. And usually, if you have big batch processing, you have a delivery lag in this amount. If you have a daily tables, usually to provide a daily table, you need to end the day and add 5 to 6 hours for composing this table at the end of the day, something like this. And I was like quite shocked about all this situation because before this, I only worked with a moderate amount of data. I use like classical databases, MS SQL, Oracle, Postgres, and they usually, if you have 100 gigabytes of data in it, you have already big data. But once I saw the real big data, it was for me a bit shocking, especially the technology they use, the approaches they use, because it's quite different. And they don't use anything like actual applications, it's just a bunch of Python scripts here and there that run everything. And no one actually understands how it works because it's 15 years of history. A lot of people change, a lot of people go and in. It somehow works. You can kind of understand how it works, but overall, it's quite complex and fragile system. Yeah, and it was my first touch with the big data world, kind of like this.
And given that trial by fire of figuring out how to manage this data transfer, the challenges associated with it, you decided that you actually wanted to invest in it even more and continue working in that space. And I'm wondering, given that context and the work that you're doing now, what are the core foundational elements of the problem of data transfer for purposes of analytical use cases that are most challenging and the hardest to solve for?
I would say the most challenging was actually making this as self-solvable. I would say like this because initially, let give you a bigger context again, a little bit. This whole system was front-facing to actual user by a configuration in the central repository. So you have a repository. In this repository, you have a file. You have actually not one file, but files. It's a file, 5 JSON files with all configuration for the whole companies. These files like 5 megabytes of data. It's a big file, big JSON file, which is not automatically produced. It's actually produced by users. So if user want to add one new item to this pipeline, you need to commit in this file. Then the CI job will trigger some Python script. This Python script will trigger another Python script, and the whole machinery starts working by magic. But users just communicate with whole the system by changing in this JSON file. And this is self-service approach is quite good for the data engineering because at the end, if you're providing this as a service, if you as engineer who designed and developed the application, for you it's very complicated systems that do a lot of stuff, it's a lot of code. But for end user, for actual data engineer who just want to see the data in the table, it's not important. They just need to somehow set up the delivery from the point A to point B. And the idea that I come to my mind is actually what actually approaching even right now is to give the tool that can be used by people who don't really care about the details about implementation. It's just one important thing. I need to move data from point A to point B. Just do this somehow. I don't care how. I don't care. I don't care the details. The only thing I care it's about freshness of a data and consistency of a data. Just guarantee me that consistency would be there and the freshness would be not so bad. And idea of making this self-service approach is actually very core for me in our product. Actually, even right now, the ability to give this as a self-service. The only problem that once you start doing this, you start realizing that moving data from point A to point B is quite complex task, and giving this as a tool rather than like a framework for development is a bit more makes everything complicated, and make the configuration of all this pipeline extremely complex. And this actually very challenging task to give the user ability to run this. It's a first step. Then investigate and monitor this, because once you run it, you need to somehow monitor it. And once it broke, you need to add some tools for investigation and triaging and debugging. And all these pillars actually is a foundation for good service, for providing service for moving data, not just a JSON file with all configurations. And the shift from this JSON file of with a configuration to some sort of a service that you can configure on your own and use it as a tool in your daily work, it's like quite challenging.
And in your work of building these tools, trying to make a self serve capability for being able to manage those data transfers, what are some of the elements of the existing solutions in the ecosystem that you find to be lacking and that necessitated your investment in this problem and continuing to build out your own solutions?
Well, we actually started building this solution, I think, 2017, 2018. First thing that we missed is actually good library of connectors. The thing that you need to connect multiple sources, multiple different kind of sources. Actually, right now, there is a whole bunch of open source technology on the market. They kind of can provide you some capabilities. There is like Kafka Connect for connecting to the relational databases. There is Arbite for connecting non-relational databases. There is like Stitch, Meltano, Stinger, anything, everything like in this world that connect, allow you to grab data from somewhere. It's like connected to your system. But the problem that quality of these connectors usually is unpredictable, and performance is maybe an issue. For example, we have a big scale of all this stuff. We have a lot of data, and using the default connector, for example, for Visa Kafka Connect was quite expensive for us. We have to scale the system not just horizontally and vertically, but actually be able to. We should be able to run as many as possible small connectors. And usually for example, the Kafka Connect one, its most popular implementation of change data capture for the open source world, run of single connector usually require you a pretty decent virtual machine and 4 gigabytes of RAM. And if you have 2,000 databases that run these connectors, it's pretty a lot. Some of them is actually reasonable to have this 4 gigabytes of RAM inside of the cluster to allocate to this database because it's decent load. But most of them actually produce one or two rows in a minute. You still need to somehow do the transfer, and you have to think not about just scalability in terms of like how many instances you can run, but how cheap the cheapest instance is. One of the key reasons why we initially decided to go to the own implementation is to reduce the overhead that usually comes with the open source solution and make it as simple and as lean as possible, and focusing on the target connectors to make it not like a big library of connectors, but like small, but really good with a good scalability and good performance to consumption ratio. Because usually once you start something, you consume some resources. It's usually CPU and memory. Sometimes it's something else. It may also be, for example, network. But usually your bottleneck in such scenarios is CPU and memory, and you need minimize them. And having the generic solution like Kafka Connect is not efficient because it has a lot of extra overhead. And initially, right now, it's not the case, but like 5 years ago, for example, Kafka Connect can't live without Kafka, and it was a big deal because if you want to connect your database and read this data and put it to a data warehouse, you have to put a Kafka in between, no matter what. And it's actually a bit of an overhead in some cases, and we try to eliminate this extra overhead and connect them directly, because why not? And this this is another point why we decide to implement it on our own.
In that space of data transfer, there are also a number of different patterns and requirements and constraints based on the type of the source system. So, change data capture, as you mentioned, is one approach to reducing the overall latency of data transfer when you're working with database engines or potentially other types of sources that have that change feed available. But then there are also situations like API endpoints where you need to be able to query the REST API to be able to get new data. Not all of those even support having some sort of incremental sync capabilities. I'm curious how that complicates the overall problem space of saying, okay, well, for these data sources, I can do this and I can make sure that I've got sub-second data transfer. But now when I'm dealing with my HubSpots or my Salesforces of the world, I have to do a different approach. And maybe some of these endpoints support incremental, other endpoints I have to do a full refresh. I'm just wondering kind of how that compounds the overall problem space.
It's make everything more complicated. Just it. That's actually the answer. You can like try to minimize it somehow. You can try to manage it, but overall, it's still goddamn complex. Internally, we have like a huge matrix of compatibility of different connector. Like this connector compatible with these features. This connector compatible with these features, and then we can, when we compile them, we say that this transfer, like source and target endpoint pair of the source and target endpoint, compatible with those features because they have the compatibility matrix intact. In fact, we actually the idea that we've concentrated on a selected set of connectors give us an ability to tune a little bit our approach. And initially, we just have one. It was the first iteration of a service. We have CDC and nothing else. Then we start adding the features one by one, compatibilities features like one by one. First, we add the backfill functionality, which we call a snapshot. And this backfill functionality, then we combine with a replication and CDC. So you backfill and then replicate. Then we start realizing that not everyone contains the change streams, and we're adding the incremental snapshot. And right now we have like all set of options available. But initially we start with a low point. Like the first point was a change data capture. I think in the most tools, the change data capture is the most complicated approach because it requires more detailed implementation of one particular connector. But we start with the hardest one and just adding the anything else around it. And we build everything around this concept of change data capture. And what we try to do is utilize the same approach any other way of reading data. So we imagine any database as a stream of changes, and this actually simplify the design, overall design of a system, and give us ability to build this extra feature easier. So stream of changes, it's simple concept. For CDC, it's more or less natural. For snapshot, it's not so natural. But what we say is that like, okay, what is the difference between a snapshot and change data capture? The only difference, like there is a stream of changes, but at some point it ends. That means that your snapshot is ended. You read all your data. And if you have a CDC, this is infinite process. Same for incremental things, actually. This incremental thing is just infinite loop of changing stuff. It's still a stream of changes, but these changes have more granular burst nature. At some point, they start reading new data, burst you new piece of data in this stream, and then like sleep for a while. So having this in the core of a system, this concept of a stream of events is actually helpful for us. Another thing that we actually designed, it was quite okay concept that we choose at the beginning, and it right now a bit helpful for us, is treating everything as events and treating any change as a logical event, and logical event bounded to a string, bounded to a row, one particular row, and this row can be bounded to a table. Initially, we think it's like more than enough for us, but once we start adding more features, we add a concept called technical events, and these technical events give us the ability to add extra features to the pipeline. So overall, we have just a pipeline, like a stream of events, infinite stream of events. It can be finite if you have like a snapshot, but for code itself, it's not a big deal. It's not there is no difference. But in this infinite stream, there is like a checkpoints, for example, or maybe some events for some technical details. Give a copy of data, for example, or run the DBT transform in or something like this. These technical events give us ability to inject functionality on this stream and give it like a flexibility to add the functionality. So the core concept, like to summarize all of this, is treat everything as a stream of events, and treat events as a event. So they can be either a row or something not related to a row. Some events for non-data related activity, like transaction starts, transaction ends. It's events, but there is no data. Data somewhere in between. But these transactional events allow us to give more guarantees for actual users, like for moving data on a transactional side. So we have transaction boundaries intact, something like this.
This episode is brought to you by Datafold, a testing automation platform for data engineers that finds data quality issues for every part of your data workflow, from migration to deployment. Datafold has recently launched a 3-in-1 product experience to support accelerated data migrations. With Datafold, you can seamlessly plan, translate, and validate data across systems, massively accelerating your migration project. Datafold leverages cross-database diffing to compare tables across environments in seconds, column-level lineage for smarter migration planning, and a SQL translator to make moving your SQL scripts easier. Learn more about Datafold by visiting dataengineeringpodcast.com/Datafold today. Given that core assumption and the core logical foundation of these streams of changes for the situation where you do have a data source that will only give you a block of data, and every time you ask for it, it's maybe the same block of data with a few new things in it. I'm curious how you think about trying to map that into the set of changes. Do you then have to maintain history of this is the block of data they gave us last time, and now we're just going to remove any duplicates and only add the new things to the change set? Or I'm just curious how you think about mapping that into that problem space.
Yeah, actually, it's both way. The first thing first, you need to treat every block data as a block data. But sometimes you want to shortcut extra cost, because reading this block data is not cheap. It's not for free, and you need to store somewhere the cursor stuff, so you know the checkpoints. And these checkpoints can be used as a part of a query or API for your source, to not like just grabbing this data in the first place. And this is actually concept that we utilize for incremental snapshot a lot. So we're storing a cursor and then use this cursor to minimize the amount of data for the next iteration. So we not just read everything, we just read smaller. For replication, it's even easier. Once we receive an answer from a target database that everything is written, we can move the cursor of our change stream a little bit further and continue reading. The only tricky part here is on restart, and this is like the tricky question appears. It's a question about delivery semantics. It's usually important one, and initially we aimed to the at least one delivery semantic. So every time if something goes to the failure, we restart our worker, and this actually give us some duplicates of a data, because we send something to a target database but not receive acknowledgement, and this acknowledgement is in a gray area. It can be either not delivered because it's okay, it's not delivered, but sometimes it's written, but we don't know about this yet. And the reread stuff from the source database give us a duplicate of this amount of data. What actually can be done with this? Actually, nothing can be done particularly. The only thing that can help is utilizing transaction capabilities of a target database to store some sort of marks on this target database in a transactional way, and remove these items from a write batch on a target side. So you still read this data a little bit more, like excessive data, but you should not write this in a target database to prevent duplication. In most cases, it's not a big deal because you have a primary case. Primary case duplication works best for almost any cases if you have a primary case, but not every database has a primary key. For example, S3, which we actually treat S3 as a database, is not contains any primary key duplication. So we need to invent some sort of a logic around it. But it can be implemented if you have a right concept in core of this logical event. And if your logical event contain some sort of sequence inside of it, you can easily deduplicate data based on this sequence. Most of change streams contain sort of a sequence number, and you can just utilize the sequence number to deduplicate stuff on target database. And we actually utilize it a lot. We provide for all changes the sequence number in it and just deduplicate the sequence number based on the sequence number on a target site.
And now moving to the consumption side of a transfer service where you say, I just want to make sure that my data gets from over here to over there. I don't care about all of these details. I just want to be able to click a button or say, this is what I need, and everything just happens. And I'm curious, as you have been working through this problem, building a product around enabling that interaction case, what are some of the sharp edges that you've had to deal with and manage and develop and engineer around to be able to give that end user experience of not having to care about all of these vagaries of the underlying technical implementations and the failure cases and recovery and retries?
I would say that what I learned from all this stuff is happy path is easy. The simple stuff works pretty straightforward, but there is like edge cases, and edge cases is really hard. The first problematic thing that we actually faced on our journey to implement this self-service kind of magically scaled solution is sometimes user don't want to scale. Sometimes the scalability should be more controlled, etc. What I mean by this is the transfer itself capable to read any amount of data from a source database, just give us enough throughput. And the problem, if user don't think about this like throughput problematic, we can use all throughput from database, and there is no more left for any other users. In some cases, it's okay if we are only user of this data, but I think it's rarely a case. So, for things that I learned that actually this magic should be controllable. User can actually control our scalability points. We provide some insights, some settings that user can actually adjust based on their needs. Rather small one, so they don't want to run more than one or two concurrent queries on top of it. So they can specify, I want to limit your capabilities to two concurrent connections. Deal with it. And then we should do as much as possible with this limitation. So users should provide us some limitation, and we provide them this ability to give this limitation. The only thing that hard in this scenario is that, like, explain to a user how they, because as I already mentioned, most of data engineers don't want to think about the complicated stuff like, okay, my Postgres is overloaded, what should I do with it? So we need like a lot of examples, best practice, and most importantly, reasonable defaults. So I would say in 80%, maybe even 90% of a case, user don't change our defaults, and this is more than enough. But having these defaults is a very hard one. You should have a lot of exploitation expertise of the overall system to understand the best practice and put it in the right place. So we have a quite smart default that actually adjusted based on your target and source databases, based on your type of a transfer, amount of a tables, etc. And these defaults actually hard to pick, hard to adjust, but user can adjust them if they want. But in most cases, they shouldn't do this.
And as you have moved beyond just the initial capabilities of I have the system, it will work, I can do A, B, and C with it, to now I need to actually run this at scale. I need to make sure that I can automatically provision capacity as new people come in or as their use cases grow. What are some of the challenges of operationalizing this complexity while still providing an accessible and enjoyable end user experience?
I would say that main challenge here is providing this is easy, but you should keep track of your costs because once you provide something as a service, like you're hiding some costs, you're hiding CPU, you're hiding compute under the hood. So users don't think about this, but you should think about this. So you should have a lot of monitorings in place. You should have a shift duty for your engineers, so your engineers always on call because your system became a critical one. If something is broken in your system, a lot of people can be affected. So you should always take a look on this. Someone should be always online. Someone should be always on call. So on call is important. Also important is monitoring and alerts. So everything should be automated. Some weird behaviors should be automated. Right now, we don't have like enough, in my opinion, alerts. A lot of stuff just exploring just by observing the monitoring. You see a strange pattern on the monitoring, and you then go to investigation, and then maybe find some bug, maybe some interesting use case, etc. And another thing that is important to give a scalable experience is providing building service with runtime agnostic in mind. We build our system initially as a runtime agnostic one, so anything that can run the Docker container is our runtime, and we can host on top of anything. And the only thing that we need to care is that we have enough capacity of this underlying system. Right now, hopefully, we have AWS, GCP, Azure that take a headache of thinking about actual physical machines out of our heads. So at least this point is solved, but you still need to manage alerts for costs, for amount of virtual machine, etc. This is still quite important, because once I joined the company back in the days, we host all this complex stuff or complex solution on the physical machines in the physical data centers. We have like several big data centers with actual machines in it, and sometimes failures was not because we don't have like good code, as maybe not enough optimization, but sometimes just too many traffics come into the system and we can't scale it because there is no more physical machines available in this particular data center. Hopefully right now with the clouds, it's not so painful to scale up and scale down, because you don't need to buy and wait until the physical machines come to your warehouse where your data center located, because sometimes it can be a quite problematic to scale a solution if you run this not runtime agnostic, not in the clouds.
Data lakes are notoriously complex. For data engineers who battle to build and scale high-quality data workflows on the data lake, Starburst powers petabyte-scale SQL analytics fast, at a fraction of the cost of traditional methods, so that you can meet all of your data needs, ranging from AI to data applications to complete analytics. Trusted by teams of all sizes, including Comcast and DoorDash, Starburst is a data lake analytics platform that delivers the adaptability and flexibility a lakehouse ecosystem promises. And Starburst does all of this on an open architecture, with first-class support for Apache Iceberg, Delta Lake, and Hoodie, so you always maintain ownership of your data. Want to see Starburst in action? Go to dataengineeringpodcast.com/starburst and get $500 in credits to try Starburst Galaxy today, the easiest and fastest way to get started using Trino. Another aspect of complexity as you scale is not just the throughput capabilities of I can handle X number of gigabytes per second or I can handle X number of users, but there's also the scaling of additional capabilities, additional complexity, as you move beyond the initial focus of I need to be able to manage change data capture. I also need to be able to start adding functionality around maybe API sources. How does the combination of operationalized system that your customers depend on with the need to be able to continue feature development and overall improvement make the development process harder? What are the aspects that cause you to have to move slower than you did at the beginning? Just wondering how you think about the evolution of the system and being able to design and architect it in a way that doesn't cause you to stagnate and have to stop development to be able to make improvements.
Yeah, that's a hard one. It's a tough question actually, because building is a scalable solution that can run in the cloud, that can scale on 1,000 customers. It's not that hard if you build it like hard-tailed, focused on a couple connectors. But we actually focused with a grow of connector base, and the main thing that actually give us this ability is two concepts. First concept is pluggability. We define in our system in architecture certain extensibility points that actually can be used as extension, and build as much as possible inside of a core. Like this core is working with just an abstract concept. They don't know anything about one particular database, one particular feature, etc. This is stuff that is common for everyone. And then we have a plugins that implement certain of aspects of connectors, and these plugins in total compose a connector that connect to the database, to API source, to a target, to the storage, etc. And this pluggability is extremely important if you try to build a scalable in terms of a development solution, because scale of features is important. And another aspect that actually is important, being just a pluggable system is not enough. You have to have a lot of infrastructure for unit testing and component tests. And we have extensive support of tests, and we test everything, test a lot of excessive stuff. And initially, we design like a sort of a test framework for our connectors, and it gives us ability to run a test and build a new feature without running our solution. So enabling sort of extreme programming practice, which is like test-driven development. We in some cases, like I would say in most cases, it may be easier to write a test rather than doing something different, like debugging it locally or maybe on some development stance. Sometimes it's easier to just write a test, make it green, initially make it red, then make it green, and then deploy the feature, and you have such flexibility and easiness. So in which we invest a lot of test infrastructure to improve developer experience, because developer experience, if you talk about the scaling in the development efforts, it's extremely important, and we invest a lot in development experience, to be honest. So two main pillars: the pluggable architecture, make this everything as pluggable as possible, and second point is a development experience and test infrastructure. I think this is our approach. I would say our current team is quite small for the amount of code that we have, and the only reason why we're still able to support this huge code base is because a lot of tests. Just tests give us this assurance that everything is more or less fine. We have quite big code base, to be honest.
And when I was looking at the data transfer product that you're building, I noticed that in addition to the change data capture functionality, you're also adding support for being able to use some of the Airbyte connectors for some of that long tail of capability, bringing us back to your point earlier about when you first started, there wasn't a lot of availability of open source capabilities
Mhm.
for some of these source and destination connectors. I'm wondering what your overall thinking is about the current state of that ecosystem, what it is about the set of Airbyte connectors that makes it worth integrating with that, what your overall thinking is about the potential for future evolution and development in that space, and maybe some of the considerations or concerns that you have or that your customers should be thinking about as they decide which of those connectors to actually bring on board.
I would say right now the state of the data engineering in terms of open source is a lot better than like 5 years ago, even a couple years ago. It's evolving quickly, and I think one of the most important projects in all this bringing the engineering in a good quality is, I think, Airbyte is a biggest win in terms of open source community. The quality of Airbyte evolving in the last year a lot. It's become a lot more stable, a lot less failures, random failures of connectors, but yet it still require a lot of engineering efforts to run this and perfectly. Uh, Per my experience, running Airbyte connectors require you at least a couple days of investigating how it works and reading the documentation, and then you can finally run it. This is, I think, is unavoidable because some connectors is just hard to set up. Like you need to run tokens, you need to prepare right scopes, etc. But overall, it's working and it's good. The only one visible flaw from Airbyte perspective is excessive cost that come with Airbyte. The design of Airbyte built in this extreme pluggability idea. What we also do as a inside of this as a pluggable design, but we do some shortcuts for us to gain a little bit more performance. So Airbyte itself internally wrap everything in a Docker container and communicate between source and the target via pipe. or file. So at least you have at least one serialization and deserialization in between, and they use this pipe structure to communicate and decouple actually source and the target, which is a good, because source can be written in one language in wrapped in Docker container, and target in another language in wrapped in Docker container, which is extremely good for development scalability. So you can write a lot of connectors easily. You can write connectors in JavaScript, in Python, in Go, in Rust, in whatever you want. But this actually brings another point. Another pain point is that as a side effect of such flexibility, you have performance slowdown. You have this bottleneck, which is a file usually between source and the target, and this serialization, deserialization, especially if you have a Python connector, and most of connectors written in Airbyte is a Python-based connectors. You have this bottleneck of serializing the data on a disk and then reading this data and deserializing back. We internally read everything in Go, and Go extremely good for running performant application, and we don't serialize data in between. We use only in-memory structures, and this give us huge performance boost for our native connectors. But writing these connectors is harder because it's not just a random Python code that you bring in your application and wrap in Docker container. This limit our capabilities. I think in modern world it's like a trade-off right now between scalability of development and scalability of application, because Arbeit gives us extra cost and you can't unavoid it. Another thing I would say is that right now there is still a plenty of open questions in terms of implementation of change data capture. Right now, the implementation of change data capture in Arbeit is not so good. It still have some flaws and problems in and it's actually still quite costly in terms of resource consumption, and running the classical change data capture of a pretty cold database which change like once in a while is still extremely expensive. And this is still a bit problem, because sometimes, and I would say most of the times, the open source community mostly thinking about growing in a horizontal space, like improving amount of connectors. And I think it's a good focus in terms of Arabyte, because they actually attract a lot of people by saying we have all connectors that you want, and it's actually kind of true. I don't remember how exact amount of connectors they support right now, but one particular connector can be improved as well, and sometimes you need to invest a lot of times in these connectors, and some connectors should be extremely fine-tuned to the extreme, because if you grabbing data from API, you don't care a lot about the performance, because API not provide like terabytes of data. But if you reading data from S3 bucket and try to move them in a, for example, Cassandra, you have to think about performance, because in S3 bucket you usually have a terabytes or maybe petabytes of data, and moving this petabyte of data with code that's somewhere in between serialized and deserialized data twice with a Python code is extremely inefficient. And you still need to think about this if you want to scale vertically on one particular pair of database. Yeah. But overall, current state of the world is quite amazing. I do like a lot Arbeit as a concept, as a product, and the overall do like a big fan of Arbeit, to be honest.
With the work that you've done in this space of managing data transfer, trying to productionize and productize it, what are some of the lessons that you have learned in the process about how best to design systems to be conducive to data transfer, or how to architect analytical pipelines to maybe minimize the need to actually move data? I'm just curious, what are some of the learnings that you've had from this experience that have influenced the way that you think about how to do data engineering overall?
I would say the main lesson I learned is like keep it simple. I have on my past experience a lot of over engineering data pipelines with a thousands, not even like maybe even tens of thousands steps in a graph, like Airflow graph with a tens of thousands steps in it, just to build a table. I like the direction that right now all data movements, all data engineering is moving. It's leaning in towards the simplification of everything. I do like the shift that made like a couple years ago from ETL to ELT, and I would say main lesson that should learn by data engineers from all the sides, like uh, try to be as simple as possible. And making data transformation is exceptionally hard, and try to avoid them as much as possible, and try to delay them as much as possible. But by this I mean that don't try to build complex pipeline of transformation. Usually it very fragile constructions. Sometimes it's necessary for sure, but if you can avoid this, it's better to be avoided. And modern approach of transforming data on a target site, like dbt or something similar, I think is superior if you have enough computing resources. I do understand that modern approach with this dbt stuff with a snowflake and databricks sometimes cost a lot, but not every database is a snowflakes. And also another interesting topic, I would suggest to try as much as possible build everything on top of open source stuff rather than building around the vendors and proprietary solutions, because vendors, even if it costs not a lot right now, it may cost a lot in the future once they understand that you're already on a hook and you can't avoid them. Vendor lock is extremely harmful in a data space, and I think right now a lot of harm was done by the overuse of a snowflake on a lot of cases. It's not needed, to be honest. A snowflake is extremely capable solution, but it's shouldn't be a default one, because you can do done a lot of stuff just in the Postgres. If you can fit your data in a Postgres, use a Postgres. Another interesting insight from my side, because I'm internally big fan of also PostgreSQL, and I think that anything below the 1 terabyte of data should live in Postgres and not leave it like just use Postgres. It's enough for you. My marketing manager would angry about this, because we're trying to provide ClickHouse as a service. But in a lot of cases, ClickHouse is a perfect database, but not in any case, every cases. And another thing that I would suggest is like there is no silver bullet. Snowflake is not silver bullet. It's a golden bullet. It's cost a little bit more, but be ready to be flexible in your tools, choice of tools, and not try to keep them simple, but yet don't stick to them too much. The open source solutions usually easier to abandon, and having this ability to abandon your solution if you understand that it's not work well for you, it's important. Just give you a little bit of freedom of choice, like some gap here. Try to build this, your pipelines, your systems, your data ingestion workflow as abundable as possible, so you can just like delete it and create once again on different rails with a different technology stack. What else I can suggest? Don't overuse Python.
And in your experience of working in this space, figuring out how to build these solutions, working with customers, what are some of the most interesting or innovative or unexpected ways that you've seen this challenge of data transfer addressed?
Oh, I have a perfect example. A perfect example. So I have a customers, which is quite interesting one. They designing a self-driving cars. Self-driving cars is the training model, basically. So there is a car, a lot of fancy stuff on top of this, with leaders, with cameras, etc. And inside of it is just a big computer with a robotic OS that collect all this information and somehow to analyze it. And they have a challenge task. Each machine, each car actually, like machine car, because inside of it just a computer. Each car goes around the city, collects this telemetry information, and somehow they need to analyze it centrally on the big cluster. And they need to move this data from machine on the ground, from a car, to the cloud somehow to analyze them later by machine learning guys or data engineers. And how to do this, because usually machine on the cities has a very limited capabilities of internet connectivity. You have like a 3G, maybe 5G in a good weather, capabilities like cell connectivity, nothing else. So what they do, they split data into two pieces, like important one, a pre-aggregated one, is collected on a car itself and sent it via mobile cell to the cloud somehow by simple HTTP call. It was not so complicated. So they have a challenge that they need to aggregate somehow information inside of a car before they're sending this. So what they do, they install a ClickHouse on the machine, on the car itself, and start querying the ClickHouse to do aggregates of a data that collected by this write and sending to the cloud. But then they need to analyze this information at whole with rough information, not aggregated one. But how to achieve this? So they park machine in a garage, and what they did is they connect machine to the proper network, to the LAN network, and once the machine become in LAN network, they connect the ClickHouse as a node of a ClickHouse that run inside of a machine to the cluster of a ClickHouse, and they start to replicate the data. And once machine in a car in a garage, they replicate data. Once data is replicated, they go again for write. And this was like the strangest cluster that I saw in my life, because each machine is just a node in a cluster, and once the machine come back to garage, the node become a synchronized one. And once machine in a city, it's just detached node. It's like goes offline by some reason, and it's not just because outage. It's because they exploring the world, and it was very interesting way of solving this problem, because initially they tried to build a very complex like graph based Python scripts with a iflow in it, but it was so clunky and not robust one. They always failed. Like machine come to the garage, the graph is failed because of some bug in the scripts, and it was hard to implement. And they don't want to work on this particular area. They want to focus on a machine itself, on a sensors, on a machine learning, and all interesting stuff. And this technical stuff was not interesting to them, and they like come to this interesting approach of using a machine as a node in a cluster. The machine itself, like car, actual car with a wheel in it.
Yeah, it's definitely a very cool and different approach to that problem. And you've definitely built a very interesting product, very capable product, but for people who are trying to figure out how do I want to get my data from point A to point B, what are the cases where the DoubleCloud data transfer product is the wrong choice?
That's actually interesting. I would say that if you have data dispersed in a lot of different systems, like API stuff, I would suggest better to use a vanilla Airbyte one. Because we initially internally try to minimize amount of support work that come to us, and therefore not open every Airbyte connector that have in the market. We just pre-select several most prominent and stable one. And so if you have like a huge different sources like Twilio API, some Zendesk API, and so on and so on. We have dozens of such. I would suggest you to just use Airbyte, just because it's easier to understand this without the middleman. Because in this case, these API sources, first of all, they will be hidden because we don't show the all API sources from Airbyte. And second of all, even if we expose it, we will be a middleman here. And we more focused on a classical movement from a more database style stuff rather than API stuff. So if you have just an API sources, just use API Airbyte here. It would be better for you to evolve.
And as you continue to build out the DoubleCloud data transfer product, invest further in its evolution, add new capabilities, what are some of the things you have planned for the near to medium term, or any particular projects or problem areas you're excited to explore?
Well, we have a lot of in mind. One of approach that we actually investigating right now, it's not yet defined, but we thinking about this quite heavily. It's open sourcing this stuff. open sourcing our data plane to make this publicly available, because code itself is pretty agnostic. It can be reused by community itself, and actually get some love from a community and some bug fixes, to be honest, and some bug reports, to be honest, as well. Another thing that we try to invest a lot is improving in terms of usability and debuggability, allowing more information about what happens inside, what can be goes wrong, how to can you can fix it, because usually a lot of stuff can go wrong here, and errors need to be fixed mostly on a source or target side by actual customers, like password is incorrect, network connectivity is not set up correctly, etc. And we try to improve our debuggability here. And another big chunk of our improvements, what we want to do is adding the transformation capabilities. We right now introduce in a memory transformation with SQL queries. We use a lot of a ClickHouse internally as a internal engine, and it's quite powerful tool. And we try to improve this area as well. And what another focus that we have is adding more native connectors, that you read by ourselves, that not is inherited by Airbyte, that designed specifically to transfer petabytes of data. And one of these connectors, like Iceberg, Delta Lake, and all the tree-based connectors, we already have pretty good compatibility with them, and we just want to improve this because Airbyte itself is good with a small amount of data here, but with a petabyte scale, it's not gonna work. And we wanted to invest some our expertise to provide ability to move huge, extremely huge delta table or iceberg tables from point A to point B. Because usually, if you have this kind of tables, you have a lot of data, and it's not like gigabytes, it's not even terabytes, sometimes it's even a petabytes, and we want to move them as fast as possible. Yeah, that's actually three our main focuses right now. It's like debuggability, native connectors for extreme scale, and possible open source. Yeah.
Are there any other aspects of the overall challenges of data transfer and the work that you have been doing on the DoubleCloud product that we didn't discuss yet that you would like to cover before we close out the show?
I would say interesting aspects is running something in a cloud, especially once you start to run this in isolation. I would say sometimes data engineers and data engineering people doesn't give enough attention to the network isolation, and network isolation is hard. A lot of tools nowadays not provide you proper network isolation. They run somewhere in the cloud, and you need to expose your data sources to the internet. And I hear a lot of complaints from security people who actually run this stuff, that exposing something to the internet is a bad idea. And once we implement the transfer in a AWS and GCP runtimes, we spent a heck a lot of time to provide the transfer and at a scale and a cheap cost, and inside of network isolation, inside of your private nets. And networking is hard, even for the engineers that you specialized in networking. But data engineers still need to understand the network some sort of. You still need to know that your database is not just exposed somewhere. If you are able to access your database from your local laptop, it's not means that everyone can do so. Most probably you have a VPN somewhere, and connecting 2 points in your data landmark is can be hard if these 2 points in a different VPC or different cloud providers. Connecting cloud providers itself, it's quite a challengeable task, and making this compliant is even more challengeable task. Yeah. So in this, if you are a data engineer nowadays, just invest a little of your time to understand what is the private nets, what is your networking stack of your current company, and all this stuff, because networking is hard and it still need to be managed. It still need to be handled by someone. And if it's handled not by data guy, he will just like forbid every access to you, and it would be a painful to enable this back again.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
It's a hard question. I would say the biggest gap here right now is I would say out of box cloud native solutions that you can host on yourself. The closest to one to this area is Arbite, but it's not like really cloud native. It's run everything on the same node on the same cluster, but running anything something on a scale require you running this on infrastructure as a layer level, like a bit lower level, and we don't have anything right now. Also, another thing that is a bit in a gray area right now is a data governance tool. They evolve a lot in the past years, but data governance is actually exceptionally hard because quality of a data is important, and if you just move data around, it's not enough for your business needs. You need to not just put this data in a target database. You need actually put some effort, clean up it, make it more quality one for later consumption. And data quality tools, data governance tools is extremely important. I see some tractions in this area for the past couple years. There is a couple good projects that's popped out in this area. I don't remember the names, but they mostly one of the biggest actually wins in this area that actually give a lot of flexibility is DBT tests. The DBT test is actually a good starting point for you to make a data governance. Writing tests on your data is actually important as well if you want to build a robust solution. Another interesting area that is evolving right now, it's not so problematic right now because we have good solution on the market in open source world, but data cataloging also important because seeing how data goes from point A to point B, it's extremely important on a complex system. If you have big system, it's really hard to track how this field was calculated in the first place. Where is the root cause? What there was involved, and what actually may broke? And if you broke something in between, what actually is affect? How big impact of this failure? And there is one particular set of tools that help you is a data catalogs. I think right now most popular one is open metadata. So this gap is more or less filled, but I think adoption of an open metadata and the data cataloging itself is not that high right now. So maybe would be evolved in a couple next years. The data catalog is not that hard to adopt, and it actually enables data inside of a company by a lot because they expose their data not just for data engineers but actually for business people, so they can actually explore what actually you have for later analysis. So this is important, and I think adoption of a cataloging also is a gap, not like a tooling, but the adoption of this tooling.
Absolutely. Yeah, that's a space that I'm looking to invest in next myself, so I appreciate you calling that out. Well, thank you very much for taking the time today to join me and share the work that you're doing on the data transfer product at DoubleCloud and your overall experience working in the space and building solutions to address this very necessary problem. Appreciate all of the time and energy that you've putting into that, and I hope you enjoy the rest of your day.
Oh, thank you. It was a pleasure to meet you as well.
Thank you for listening. Don't forget to check out our other shows, Podcast.init, which covers the Python language, its community, and the innovative ways it is being used, and the Machine Learning Podcast, which helps you go from idea to production with machine learning. Visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.